Hi again. The next topic we are going to talk about is the sampling distribution. So remember, we are estimating, we are guessing, inferring about the population using the sample. And the sample is always random because sample is generated from an experiment of random sampling. So if you resample everything, then your sample will be totally different. In that sense, there is a randomness. So then the problem here is when you estimate the population using the sample, something you calculate from the sample, then the estimator is still random, which is not a surprise because you know that an estimator has random errors. The error itself is random. So then, how can we handle that? There is no way. You cannot you cannot get rid of the error from an estimator. There is no perfect estimator in the world. So, so, uh, or you may put it this way: to remove the random error, if you want to kill the random error, the only possible way is to have infinite number of uh, observations or super large data. Very huge data will result in an estimator with a very small random error. That's possible, but increasing the sample size is not usually it's not available because of usually financial reasons. So that's not our option. So given the data, we need to understand how to utilize the data. And then what we do here is we try to understand the distribution of the random error. There is a random error. Always there is a random error. We cannot remove that. Then let's study that. So that's the approach. Let me start from the idea of sampling distribution. So the sampling distribution is I will think about this example. Another the simplest possible example, coin toss. Coin toss. When I say coin toss, it is an experiment. So throw a coin, and 50% heads, 50% tail is observed, right? So that's one experiment and one outcome. And if you throw another coin, then you are going to get heads or tails with the same probability. So if you throw 100 coins, you are going to observe 100 observations. Then we say you repeat it. So you repeated the experiment 100 times, observe 100 outcomes. However, now we are going to use a different approach. I'm going to consider a more abstract experiment. So in the previous example, one coin is one experiment, and 100 coin is 100 experiments, which is obvious, seems obvious. But now I'm going to think it this way: you have 100 coins on your hands and throw them at once, and count how many heads you have. And I'm going to consider this 100 coins as one experiment, right? If you want to repeat, put all the coins back on your hands and throw them again, and count how many heads you have. That is second experiment. That's how we are going to consider how this is how our so for a while this is the experiment we have in mind. So, for example, it's not that difficult. If you think about two coins, so instead of throwing one coin, I will throw two coins at once. So two coins on my hand and throw them together, and then the outcomes will be 0 or zero point 0.5 or 1. So p head is the sample probability of heads. So out of two coins, how many heads you observe. So 0 or zero point 0.5 or 1, and you know their probabilities. The probability of two tails is 25%, probability of two heads is 25%, probability of one head and one tail is 50%. This is a sampling distribution. Remember, this distribution, this probability is coming from two coins, right? You consider two coins at a time. And similarly, if you consider 3 coins, if you throw 3 coins at a time, then the result will be 0, 3 tails, and 1 head, 2 tails, 2 heads, 2 heads, 1 tail, and 3 heads. There are 4 possible outcomes, and each of them have this probability. When you throw 3 coins, 2 times 2 times 2, there are 8 possible combinations, and the probabilities are given this way. So the probability of having all tails, 3 tails, is 1 over 2 times 1 over 2 times 1 over 2. So it's 1 over 8. And same here, and the other probabilities follow. So then this distribution, this probability distribution is originated from the experiment of throwing 3 coins at a time. So, right, do you see the difference? Like usually we think 1 coin is one experiment, but if you think 3 coins as one experiment, then you get different distribution. When you think about 1 coin, the probability is 50-50, 0 or 1. 0 50%, 1 50%. But when you throw 3 coins at a time, then the probability distribution becomes like this. You may extend this number to any arbitrary number. You can throw 100 coins at a time, then still it'll be much more complicated. The possibility is from 0, 1%, 2%, up to 100%. There will be 101 possible outcomes, and there must be probabilities attached to them. So then what we do here is the underlying the key idea of the sampling distribution is the new underlying experiment. Underlying experiment itself is different from the random sample the randomly choosing one outcome. Experiment is throwing n coins, or random sampling. You can think it as a random sample. And then random variable is probability of heads from n coins. So remember, random variable was defined as a function from the outcome of an experiment to some number. So in this case, you have 100 coins, and your random variable is defined as, so out of 100 results coins, you describe the results by the probability of heads. How many heads you observe out of 100 coins. So that is the random variable. And then think about the repetition of the experiment. Probability distribution, or the randomness, is generated from repetition of the experiment. And here, repetition is throwing n coins and again throwing n coins again and again and again. So if you throw n coins once, then you calculate one sample probability. And then what if you repeat the experiment? You throw n coins again, on 100 coins again, and calculate another sample probability. So if you repeat this like s times, here let me say it as s, if you repeat throwing 100 coins s number of times, then your observations will be like this. This is how you this is the imaginary data. Then if so, then when you repeat that s times, you have tossed n times s coins so far, but only we count s sample size is s, because we only have s observations, and n coins together are considered as one experiment. So the sample size is s in this scenario. And then the distribution of this experiment came from s equals to infinity. That's the population. That's the target distribution. Then you can derive the perfect distribution, the true distribution of p hat. That is the sampling distribution. Okay, let's generalize the framework the sampling distribution is based on this idea. One experiment is one random sampling. One random sampling is collecting n observations, and then, that have to include this. You calculate something out of that n observations. So collect, say, survey. Suppose that. So think about. Okay, let's put it later. So anyhow, one experiment is generating a random sampling, and calculating one number out of that. If you repeat that experiment, then you observe a different value of t, different value of the statistic. So you observe 100 people, and you calculate their average income. So observe 100 people and calculate their average income. And when you repeat the experiment, it means that you randomly survey 100 people again. Those 100 people could be totally different from those you have used before. So you observe new set of 100 people, then their average income would be different from the earlier average income. So that's the second observation of the average income. So if you repeat that again, so survey 100 people and then calculate their income, and again survey 100 people, calculate their average income, and repeat that, then in the end, theoretically, you are going to obtain the sampling distribution of the average income. Remember, the key idea is the randomness is generated from random sampling, right? The reason why you have this distribution is because of your random sampling. You random sample again and random sample again and again. So then why is it important? You may understand it as this statistic is usually an estimator, your estimator, and the sampling distribution is closely related to the population you want to understand. By the way, so then also this is important. The sampling distribution, I said sampling distribution has its own population, but this population is not the population you want to understand. The population is suppose that you want to estimate the true probability of heads. This probability distribution assumes one coin toss. So one coin toss is an experiment in this probability definition. However, in this sampling distribution, you have 100 coins are one experiment. So the underlying experiments are different in the sampling distribution and in the distribution you are interested in, right? However, they are different, but they are very closely correlated. They are related to each other, so that's why we study the sampling distribution. But however, it is just purely theoretical and abstract process, so it's really hard to understand. And I think many of PhD students don't understand this even after taking this course. I understand why you don't understand, but still it is very important. So Stark and Watson, maybe you may have heard about the famous econometricians at Harvard and Princeton. Stark and Watson, who have a famous textbook, they say in their textbook, they say understanding the sampling distribution is the most important thing to understand in the undergraduate level. At the undergraduate level, econometrics or statistics course, sampling distribution is the most important concept to learn. However, I understand it's very unlikely, but still I agree with their claim. It's important. Anyhow, sampling distribution is purely hypothetical experiment, hypothetical object theory, because you never observe the repetitions. How you cannot? So suppose that when you throw 100 coins, and if you can throw 100 coins again, I would rather throw 200 coins at a time. That will yield a better estimator. So you never observe the repetition of the sampling distribution. But however, it is purely theoretical, but we can derive or estimate the sampling distribution of this statistic from your data. It's interesting. So you don't observe anything, or you never repeat, but still you can estimate that. And from the sampling distribution, you can evaluate the properties of this estimator, right? Like for example, unbiasedness, standard error, or consistency, type 1 error or type 2 error probabilities. Those kind of properties are derived from the sampling distribution. And here I'm going to maybe finish the lecture note in the next video. Thank you for watching this video, and if you are still, if you must be confused by this concept, then how can we do? Think more about this, or maybe I recommend you to search for sampling distribution on YouTube or Google and read some other materials. They may explain better. I tried myself, but if it's not enough, not easy enough for you, then try something else to understand this. Thanks.